So good afternoon, everyone. So first of all, let me introduce myself. My name is Mattia Silvestri, and I'm currently a PhD student at the University of Bologna. Today, I will present you our work, Hybrid Offline-Online Optimization for Energy Management via Reinforcement Learning. This was a joint work with the colleague of mine, Allegra de Filippo, Federico Ruggeri, and Michele Lombardi. Okay, so let's start from the motivation behind this work. So when you are facing real-world constraint decision problem, then we have usually have to deal with uncertainty. So let's think, for example, to energy management system. Of course, if we have a forecast about the user demand, then we can play the day-ahead load, electricity load. But then during the day, we should keep the power balance on an hourly basis, for example. And of course, this uncertainty make the task harder, but we may have some information about this uncertainty. So for example, we may have historical solution, or we may know something about the probability distribution that model this uncertainty. And we can think of splitting the decision process in two parts. The first part, which we call the offline part, we take the so-called strategic decision. And this basically do not require very strict timing constraints. And for example, planning the day ahead power load. And then we have the so-called operational decision that are made online, and then they require very strict timing constraint. And so we need to take this decision very fast. Okay, and in recent work, some of the authors of this work have shown how a strong integration between these two distinct phases can be helpful, can lead to improvement both in terms of the solution quality, but also can reduce the computational cost. So I put the reference here to the work, and the overall idea of this kind of work is, well, during this offline phase, we try to perform a parameter tuning phase that allows to improve the behavior of the online algorithm that may be suboptimal for it, okay? So the contribution of our work is let's replace this offline phase with a deep reinforcement learning approach. And for the use case that we consider, that is an energy management system, we have provided two viable formulations that we will see in a while. And we also we compare this method with a state-of-the-art hybrid offline-online algorithm, but also with a complete end-to-end, let's say, full reinforcement learning-based approach. And we will see why the interplay between learning and optimization can be beneficial compared to full end-to-end approaches. Okay, so now let's see the problem, the real problem that we have faced. So in an energy management system, we need to find we have many energy resources for which we can pick of course, the energy. And we need to find the minimum cost power flows between these resources such that the user demand is satisfied. And these energy resources are combined heat and power dispatchable generation that has associated a fuel cost. But we also have an external grid from which you can buy or sell the energy according to the prices of the electricity market. But we may also have renewable energy resources, namely photovoltaic system. And the important thing here is that in our case, this photovoltaic system provide additional energy with no additional cost, okay? But at the same time, they are uncertain. What does this mean? That we may forecast what will be the production, but we are not sure about what this production will be. And also the user demand is uncertain. Again, we may, for example, forecast the user demand for the following day. We may say, well, in the late evening, the electricity demand will be higher, or in the early morning will be higher. But of course, we are not sure of this value, and we will observe it during the decision process. So this basically is how the EMS works. Our online optimization algorithm is a multi-stage optimization problem. What does this mean? Well, we consider a 24 hours day, and we split it in 15 minutes time frame, and we call these stages. And during this stage, we observe the uncertain variable, which are the photovoltaic production and the user demand. So we observe the actual value of the uncertain variables. Then we run our online algorithm that basically what it does, minimize the operational cost and cover the user demand. And then we evaluate this cost. And we repeat this procedure for all the n stages. But one thing to notice that this algorithm may be myopic. And what I mean is that it considers only the current stage and not the whole optimization problem, okay? And for example, storing energy has no direct profit. So this kind of algorithm will always end up selling all the energy. But if you think about it, this is not a reasonable behavior. What we really want is to store energy when the prices of the electricity market are low in anticipation of future higher user demand. So the idea is to introduce an additional cost that you see here, the C storage. This is not something that concrete, but this cost allows to keep into account the benefit that the storage can introduce. So this cost will be negative when storing energy is profitable or positive otherwise. And during the offline phase, we basically find the optimal value of the storage for all these stages. Okay, so here, given our forecast of the photovoltaic production and the low user demand, then we predict which are the optimal C storage values, and we plug these values in the online algorithm. Since now we have only represented our problem, now we will briefly see the state-of-the-art algorithm that we will compare our method to. And the idea of this state-of-the-art method is to, starting from the forecast, obtain many scenarios, so many realization of the uncertain variable, and then adding in the model of an optimization model of the online algorithm, the virtual cost for each of the stages for all the scenarios, okay? And then we introduce the KKT optimality condition, and then solving this overall big problem, we can obtain the optimal C storage values. And then we obtain the optimal behavior that are optimal with reference to the behavior of the online algorithm. But one thing that we need to notice is that this algorithm requires the optimization model to be convex, okay? And another thing, that the accuracy of the quality of the solution strongly depends on the number of sample scenarios. So of course, if we sample many scenarios, then the computational complexity is really high. So it has some scalability issue. So now let's describe our contribution. So the idea, as I previously said, is to replace the offline phase with a deep reinforcement learning algorithm. And we basically employ DeepRL as an instance-specific parameter tuning solver that find the optimal C storage, or at least try to find the optimal C storage. And the advantages of this method is that convexity is no longer required, and it also is better scalable compared to the previous method. And for our use case of the energy management system, we have provided two viable formulations. In the first formulation, the reinforcement learning agent set the virtual cost for all the stages all at once. Okay, and we call this approach single step in the following of the slide. The second approach instead exploits the sequential nature of the problem, and for each step it provides the virtual cost only for the current stage. But let's see a schema that maybe can help us understanding this method. So this is the single step version, predict the values of the C storage all at once, okay? So we have the forecast, and we give this forecast as input to our reinforcement learning agent, Pi, which provide all the C storage for all the stages. Then we plug this value in the online algorithm, and for each stage, we observe the realization of the uncertain variable, we evaluate the cost, we sum the cost for all the stages, and this is the reward that we provide to the agent. This is just a sum up of what I've said right now. Instead, the second formulation is really a Markovian decision process, because the reinforcement learning agent pi provides the virtual cost associated to the storage system only for the current stage. Then we plug this in the online algorithm, observing the true values of the certain variables. We evaluate the operational cost, and this is basically the reward. And the observation is a representation, an encoding of the current stage, the state of the system, and the forecast for the photovoltaic production and the user demand. And as a baseline method, we have also provided a completely learning-based solution, because this method basically directly provides the power flows, so the solution of the online optimization problem. And as you may guess, this task is really hard. And in particular, this method does not grant satisfaction of the constraint, but has to learn the constraint from the reward signal. Instead, in the previous formulation, the constraints are naturally satisfied in the method formulation itself. Okay, here we take a quick look at the data. We have a set of instances. Here we report the mean and standard deviation of the photovoltaic production and the user demands on this set of instances. As you may guess, the peak of the photovoltaic production is in the daily hours, and the peak of the user demand is in the late evening. Okay, so before diving into the results, let's see which are the methods that we compare. We compare 6 methods. The first method is the simple online algorithm that does not take into account the virtual cost associated to the storage system. So we simply run this online algorithm once we observe the realization of the certain variables. And we call this greedy heuristic. Then we compare it with the state-of-the-art offline-online optimization algorithm that it is called tuning. And with a revised version of this algorithm that relies on perfect information. This, of course, is not a realistic approach, but is only used to evaluate the optimal solution, and we call it Oracle. And then we also see the results for the method that I have described right now, so the single-step version, NDP, and the full reinforcement learning-based solution that we call RL. So let's see the result. Here on the left, we report the optimality gap. On the x-axis, we report the time required for training. Of course, for the method that are not a learning component, we simply plot an horizontal line. And in the right part, we report the time required for each training epoch for the reinforcement learning-based approaches, or the total computation time required by the other algorithms. And in the upper part of the figure here, you can see that the reinforcement learning-based approach, so only reinforcement learning, non-hybrid formulation, well, it provides a solution quality which is worse, very bad compared to the other methods. Let's see that let's pay attention that let's notice that the order of magnitudes are completely different. And in the lower part, instead, we see the other methods. And here we can see that the simple greedy heuristic, well, performs worse than the other method. So introducing this additional virtual cost that keeps into account the storage system actually helps the online algorithm to find a better quality solution. And surprisingly, the best method is the single-step version of our hybrid formulation that is able to surpass also the state-of-the-art tuning approach. And well, it's close to the Oracle, but of course, we cannot surpass we cannot reach the optimal solution. But at least that provides a good performances. So just to wrap up everything, here we have seen, let's say, a successful method that combine learning and optimization for offline-online optimization under uncertainty. And of course, our method is successful only for the use case we have tested, which is an energy management system. We have seen that the deep reinforcement learning-based approaches can outperform the current state of the art, again, for this use case. And I think what is important also is that we also surpasses the complete end-to-end reinforcement learning approach. So here, maybe we can say that an integration between learning and optimization is actually beneficial. And future works, as I previously mentioned, these are instance-specific parameter tuning, but using reinforcement learning allow us to generalize to using deep reinforcement learning, we can achieve generalization. So given a set of forecasts, we directly provide the optimal value of the virtual cost without retrain the method. So I think I'm on time. So that's it for my presentation. Thank you.
All right, so we can have questions. Yes. Have you considered using things like imitation learning for the offline, for the online part? So you mentioned that it was not as accurate enough. If I understood you correctly, that the conventional online method you use, but have you tried to convert some of that knowledge into the RL part of the online problem?
No, but the overall idea is that, of course, to use imitation learning, we need label data. And I think the advantages of reinforcement learning-based solution that we simply use a reward signal. So we can simply train this algorithm, only evaluating the cost. So the overall idea is using, train this algorithm without using supervision. Let's assume that we don't have supervision for the optimal solution.
But supervision from your method that you used, from your online method that you implemented?
Well, we didn't do that, but of course it could be beneficial. Yes. Thank you.
Yeah. Do you have any intuition for why the single step did better than the multi-step?
This is a good question.
Like the multi-step has strictly more information.
That's true. Well, let's remind that in reinforcement learning, usually we design the reward function to teach the agent what should be achieved and not how should be achieved. And if you provide a reward at each step, well, you are saying how to achieve the result. Okay, but we have also tried to provide the reward only at the very end, at the last stage, but it does not work because, of course, making reinforcement learning is not very easy. There's the exploration-exploitation dilemma. So my intuition is that the single-step version directly sees the outcome of his action. Instead, the sequential version gets stuck in a local optimum. But of course, I have not proof of it, only an intuition.
So I was wondering about data. I mean, like the model in single-step sees a lot more data.
No, all the method, well, sorry, see the same instances, and they are trying.
It's regarding to one decision. Like, yeah.
Yeah, but I tune the batch size basically to be sure that the samples seen by the single step and the NDP are the same, are comparable. I tune the.
Okay. Yeah.
Do you prune the scenarios? Because that's one thing that I was thinking in the MVP version. As you go forward, some of those scenarios that are in your inputs are clearly invalid because they're very different from what you've seen in the past. Or you just use all the scenarios at every stage in the MVP.
No, they see only the current realization of the certain variable.
But the futures, they see all the scenario futures, irregardless of how well those predicted futures agreed with what you saw in the past.
Sorry, I didn't get the.
So you've got a number of scenarios, at least the way I understand it, you've got a number of scenarios you're given as to what the future, what will happen
Yes.
to ours and the else.
Yes.
But then as you go forward, you've actually seen some of those. So you've seen that some of those scenarios might be way off, right? Because you've seen the realizations of the first time step, the second time step, the third time step. So some of your scenarios may be very different from that. And if you keep using all the scenarios, maybe you're not being very accurate, but you just use all the scenarios for the future.
Okay, well, I have to think about it, to be honest. I'm sorry.
But in the reinforcement learning, you didn't use the scenarios anymore, right?
No, not really scenarios. We call the realization, let's say, because when we take an episode, we sample a realization according to the probability distribution that model the uncertainty. So the scenario is only for the tuning approach that performs see all this scenario during the offline stuff.
Other questions? So do you have an idea to what other class of problems this form of offline online would also be applicable? Does it need a certain property of the online phase or?
No, in general, no. We can think also to apply to the dynamic WRP, but of course there is a lot of work, so we have focused on the only energy management system, but I think we should also try to apply to other class of problems like the dynamic WRP, for example.
All right. And ORP? ORP? Dynamic what?
WRP, vehicle. WRP, I'm
yeah.
sorry.
All right. Okay, no further questions. All right, thank you very much.